Hello and welcome to the first video of section 3.4 on limits at infinity. In this section, we explore the end behavior of a function. What happens at the extreme ends of a function? As the x gets larger and larger unboundedly, what are happening to the y values? Are they getting smaller? Are they getting larger? Are they fluctuating between 1 and -1 like the sine and cosine curves? Or are they approaching 0 like in the function 1 over x? When asking about the end behavior of a function, we are asking what the limit of the function is as the x values approach infinity or negative infinity. If the function can be made as close to L as we would like by choosing an x value sufficiently large. Take for example the function y equals 1 over x. The limit as x approaches infinity of 1 over x is 0. If I want a y value smaller than 1/10, I must choose an x value bigger than 10. If I want a y value smaller than 1 over 1 million, I have to choose an x value larger than 1 million. The closer the y values are to 0, the larger the x value I must choose. Therefore, as x goes to infinity, the limit of y is 0. This definition allows us to describe the end behavior of many functions. Certain functions have finite limits at infinity. Take 1 over x, whose limit at positive or negative infinity is 0. Or 1 over x squared, whose limit at positive or negative infinity is also 0. Not all limits at infinity have to be 0. The function y equals f of x depicts a function whose limit at positive or negative infinity is c. Other functions have infinite limits at infinity, like polynomials. The limit as x approaches either positive or negative infinity for x squared is positive infinity, while the limit as x approaches infinity for x cubed is infinity, and the limit as x approaches negative infinity for x cubed is negative infinity. Some functions can fail to have a limit at infinity. Periodic functions, like the trig functions, do not have a limit at infinity. The function f fails to have a limit as x approaches positive infinity, as the function appears to have greater fluctuation as x gets larger. The examples 1 over x and 1 over x squared are an important example of limits at infinity. In fact, for any positive power r, the limit as x approaches positive or negative infinity for 1 over x to the r is 0. This observation will be our best tool in calculating limits at infinity. We will use it many times, so be sure it appears large in your notes. If a limit at infinity for a function is finite, we say that the function has a horizontal asymptote at that value. That is, if the limit as x approaches negative or positive infinity equals L, then the line y equals L is a horizontal asymptote for the function. The functions 1 over x and 1 over x squared have horizontal asymptotes at y equals 0. Recall that a rational function has the form a polynomial divided by a polynomial. Many of you learned in high school how to find the horizontal asymptote of a rational function. The reasoning goes, let an be the leading coefficient and n the degree of the polynomial in the numerator, and let bn be the leading coefficient and m the degree of the polynomial in the denominator. If n is larger than m, there is no horizontal asymptote. If n equals m, then the horizontal asymptote is y equals an over bn. And if n is smaller than m, then the horizontal asymptote is y equals 0. This reasoning is supported by calculus. Take for example the rational function 2x cubed plus x minus 7 divided by x cubed minus 1. The limit as x approaches infinity for f of x can be calculated by multiplying 1 over x to the r throughout the top and bottom of the expression. Note that 3 is the degree of the denominator, so we'll multiply the top and the bottom by 1 over x cubed. Distributing 1 over x cubed in the numerator and 1 over x cubed in the denominator gives us an expression where we can take the limit as x approaches infinity. As x approaches infinity, the expression circled in red will approach 0. So when we take the limit as x approaches infinity, we find that the limit is 2. Notice that the degree of the polynomials were the same, so the limit is the ratio of the leading coefficients, 2 over 1. If we take the same example, but alter the numerator so it's 2x to the fourth plus x minus 7, so our polynomial in the numerator has degree 4. We calculate the limit as x approaches infinity in the same way. We multiply the numerator and the denominator by 1 over x cubed. 3 because it's the degree of the denominator. Distributing 1 over x cubed through the numerator and the denominator, we obtain an expression where the expressions circled in red are approaching 0 as x approaches infinity, while the expression circled in blue is approaching infinity as x approaches infinity. So as x approaches infinity, the denominator approaches 1, while the numerator is unbounded, approaching infinity. Therefore, the limit is infinity. Notice that the degree of the numerator is higher than the degree of the denominator, and the limit was infinite. Therefore, we have no horizontal asymptote. Taking a similar example but changing the numerator to 2x squared plus x minus 7, we calculate the limit as x approaches infinity in the same way. We multiply the numerator and denominator by 1 over x cubed, 3 because it's the degree of the denominator. We distribute 1 over x cubed in the numerator and the denominator, and as x approaches infinity, the expressions circled in red approach 0. Therefore, the limit as x approaches infinity for the function f is 0. Notice we have a rational function whose degree in the numerator is less than the degree of the denominator, and the horizontal asymptote is y equals 0. A final note on horizontal asymptotes. A function can pass through its horizontal asymptote. It is a common misconception that a function does not cross its horizontal asymptote. The horizontal asymptote expresses end behavior, and it doesn't dictate the behavior of the shape on the remainder of the graph. This function has a horizontal asymptote of y equals 0. The red dot, the point 0, 0, is exactly where this function crosses its horizontal asymptote. To summarize, the end behavior of a function is described by its horizontal asymptotes, which are limits at infinity of the function. Our best tool for calculating limits at infinity is the expression 1 over x to the r for positive rational values r. In the second video of this section, we will calculate additional examples of limits at infinity and discuss limits at infinity which happen to be infinite.